A general theme that will be recurring in almost every single lecture in this course is that we will see individual behaviors, often driven by self-interest, aggregate into a state across all the users, a global configuration in a social, economic, or technological networks. And sometimes it can aggregate into a fair and efficient configuration. We'll try to quantify efficiency and fairness in the course. And such a phenomenon of local behavior aggregating into a global configuration that is desirable is going to be helped by some kind of feedback signals, which could be, say, a pricing signal, or maybe a congestion signal, or maybe a collision signal. Some of these feedback are explicit. Some narrow element tells you a specific action that you need to take. Sometimes they are implicit. You measure something, for example, the current SIR at time t, and then use that implicit feedback to adjust your own individual behavior in the next iteration. Now we're going to understand the specific behavior in distributed power control from two angles now. And in that sense, we're using DPC as a way also to introduce us to the terminology and the basic notions in two powerful mathematical modeling languages. One is the language for constrained decision making called optimization theory, and the other is the language for strategic thinking by intelligent agent called game theory. Now let's start with optimization theory. This is a word that we use in our daily language. Right? We try to optimize something. We try to optimize our time, our holiday schedule, our work schedule. And if you think about it, in an optimization, you have some degree of freedom, which we will mathematically call optimization variables. You have some objectives you want to maximize or minimize. For example, maximize your employability, okay, your happiness, minimize the cost it takes to finish some task. And then you have some constraints. Without constraints, the problem would be too good to be true. This could be constraints on the time you have, on the money you have, on the energy you have. For example, when you look at your schedule this weekend, you may say, well, I can pick my variable to be spend the time taking a course like this one, or spend the time to watch a movie. And the objective function may be, well, make me as happy as possible. And the constraints, say, is you only have 24 hours in each day. Now we will see a mathematically precise, unambiguous language called optimization theory. And in each optimization problem, there are four main data fields. One is, of course, the objective. Now, in the case of transmit power control in cellular networks, the objective is to minimize the sum of the individual transmit powers. So we'll write minimize the sum of the PIs over Is. So this is a power minimal configuration, subject to the constraints that you have to achieve the target SIRs for all the users. The SIRs for each user indexed by I must be no smaller than the target gamma I. And you need this to be held not just for a single I, but for all I's. And then you need to vary the degree of freedom. In this case, obviously, it is the set of transmit powers. And everything else are constants, including the channel condition, the GIJs, the noises, NI for each receiver, and the target SIRs, gamma. Towards the end of this lecture, we'll also see what would happen if these target SIR values become variables as well. But for now, they are held constant. Now, once you have an objective function, a set of constraints, and you know what is variable and what is constant, then you have an optimization problem. Pictorially, what we are looking at in this case of transmit power control is visualizable in the following cartoon. Now, suppose we have just two users, so we can draw in a two-dimensional plane on a piece of paper slide. And the first user, SIR, is on the x-axis, the second on the y-axis. And we have a region. Okay, it's a shaded region here that denotes the set of feasible SIR values. Okay. Now, ideally, you want SIR for both users to be high. But as you know, because of interference, that is not possible. So let's just look at those SIR1, SIR2 values that are possible. And we call these the feasible SIR values. So any point inside this region, okay, is a feasible point. But there are also inferior points because I could find a way to increase SIR for both users. Okay. So any points in this region would be strictly better than this point. At the same time, every point outside the boundary is infeasible. Now, what about the points exactly on the boundaries? We call those points Pareto optimal. Now, clearly, there are infinite number of these points on the boundary, and they are all Pareto optimal. In some sense, they are not directly comparable. Okay? Points inside are feasible but inferior. Points outside are infeasible, so don't even worry about those. Our job is to find a point that's at least on the Pareto optimal boundary. That means you cannot increase one dimension without hurting the other dimension. Those points formulate or form the boundary of this region. Now, which point to pick then? That would depend on the objective function. You have to impose some other objective function in order to pick exactly the point that you like most. Now, later we will see this theme of trade-off. Okay? Trade-off in this case between two users, SIR, and in general, the trade-off between any competing users in a social, economic, or technological networks. And we'll always want to operate on the Pareto optimal boundary. At least pick a point that is Pareto optimal. You cannot make one user happier without making another user less happy.